All right, so let's, in the last lecture, we were looking at how this enhancement mode MOSFET, how it works. And what was very interesting about this particular device was that by applying a gate voltage, you can take the surface and start from a surface which is p-type with carrier density holes 10 to the power 16, electrons 10 to the power 4. You can start with a p-type surface and then apply a gate voltage, and you can make the surface intrinsic, n is equal to p, and you can make the surface n-type, where the number of electrons is more than number of holes. And not only that, you can make the surface strongly n-type, or you can create a strong inversion layer, a layer of electrons at the surface here. And so this was the, in terms of a plot, this is what is happening as you apply a larger and larger voltage. You decrease the hole density and you increase the electron density. And I've not shown the scale, but later on what you would see is that the scale here is a semi-log scale, in the sense that this is a log axis and this is a linear axis. So what you're able to do is change the hole density. As you can see from the previous diagram, you can see that the hole density is really changing from 10 power 16 to 10 to the power 4. You can see it's 12 orders of magnitude here. So this is all an exponential decrease here. And similarly, the electron density is increasing exponentially with the gate voltage here. But after a while, once, so we also defined a value called the threshold voltage. So threshold voltage was where we said was, if you apply a gate voltage larger than threshold voltage, then what you end up getting is a strong layer of inversion at the surface, and significant current begins to flow here. So that's the idea behind VT is. Below VT, the carrier densities, electron densities are small, and although current flows, the current is also small here. All right. So let's continue then with a little bit more detail here. The first thing is, I've been saying that when you apply a gate voltage equal to 0, what you end up is that it's like a normal p-type semiconductor. There are no fields and all that. This is not true in practice. Whenever you take two different materials, which we have seen in the previous semester, whenever you take two different materials, let's say you take p-type silicon and n-type silicon, and you put them into contact, what we call as a contact potential develops between the two semiconductors. Right? In a PN junction, we saw there was a built-in voltage. And that's a general statement. You take any two materials, they will have different work functions and all that. When you put them into contact, a potential develops here. So even though you don't apply anything, remember in a PN junction, P side is ground, N side is ground. You don't apply any external voltage, but internally a voltage develops because the two semiconductors are different. The two materials are different here. So here also, when we look at, we have a gate for the, we have a gate on one side, metal, and we have a semiconductor. And when you put the two of them together, what happens is that there is a sort of built-in voltage between the metal here and the semiconductor here. Built-in voltage is there. So what needs to happen is that you have to apply a voltage in order to cancel the effects of built-in voltage and thereby have this particular layer so that there are no fields inside the semiconductor. So what is being said is that because of differences in the nature of metal and the semiconductor here, even if you apply Vg equal to 0, there is a field inside the device, a built-in field. And if there is a field inside the device, remember, if there's an electrostatic field, then the surface would be, depending on the nature of the field, the surface would maybe depleted, number of holes may be less and all that. Okay, so it's not a a normal p-type semiconductor. When you apply a field, we have already seen what happens inside the semiconductor here. So what we are saying is that you need to apply an external voltage, Vg equal to V flat band. In order to, flat bands means, if the bands are flat, it means the energy is not changing, potential energy is not changing, voltage is not changing. And if voltage is not changing, it implies, if voltage is flat with respect to position, it implies zero electric field. Okay, so what we are saying is that there is at zero gate voltage, there is in general, a built-in field, You have to apply a gate voltage equal to V flat band in order to make the electric field 0. So whatever we were saying earlier, that at Vg equal to 0 there is no field and things like that, we have to correct that and say that Vg equal to V flat band. You have to apply Vg equal to V flat band in order to create, start from a situation where there are no fields, and at that point the number of holes at the surface is like a normal p-type semiconductor. There are no fields, nothing here. So holes at the surface is same as holes in the bulk, and if the doping is 10 per 16, the number of holes is also 10 per 16. Okay, so that's the starting point. Just to keep things simple, I didn't want to talk about flat band and all that right at the outset, but so let's introduce that and say that at Vg equal to V flat band, then the p-type semiconductor is act like a normal p-type semiconductor with holes and electrons as expected according to the doping here. Now, so when Vg greater than V flat band, when you apply a voltage larger than flat band, and note that we are applying a positive voltage here, so you create a field here which starts from the metal and goes into the semiconductor here, and that field now begins to, as we saw, push away the holes from the surface here, and you start creating a positive charge here, and therefore you create a layer which is depleted of holes. We saw that once you deplete the holes, you increase the number of electrons, but the number of electrons is also very small. When Vg is larger than V flat band and Vg is less than the threshold voltage. We said threshold voltage is the point beyond which, if you make Vg larger than threshold voltage, you start getting a strong inversion layer. Okay, so in this range, Vg larger than V flat band and Vg less than threshold voltage here. So there is a range here where the surface and the region close to it is depleted of carriers, depleted of both holes, and electrons are also very small. Okay, so we call this a depletion region here. Holes are depleted from the surface, and although Ns electron density at the surface is larger than electron density at the bulk, electron density is also small. When Vg greater than threshold voltage, now note the difference between the two. Here when I drew a depletion layer, this is the boundary of depletion layer, I showed all these acceptor ions. I'm not showing much holes have been depleted, and I'm also not showing any electrons here. They're also very small in number. But once you exceed Vg greater than VTHN, then in addition to this region which is depleted, I'm showing a strong inversion layer also, a sheet of electrons present there. Okay, so you have to apply voltages larger than the threshold voltage in order to create a strong inversion layer. So we are saying that in a MOS capacitor there are two interesting voltages. One is the flat band voltage. When you apply Vg equal to V flat band, there are no fields. P-type semiconductor is as it is, and then there is a Vg greater than V threshold when a strong inversion layer forms here. Electrons are accumulated at the surface. Electron density is even much larger than the hole density in the bulk here. You can also apply Vg greater than less than V flat band. In this case, when you apply Vg less than V flat band, the fields are going to go in this direction. All right, well, they'll start from here and they'll go up. For Vg equal to V flat band, field was 0. For Vg greater than V flat band, the fields start from metal and go into the semiconductor. For Vg less than V flat band, the fields start from the semiconductor and go into the metal here. So what you're doing is, when you do that, you want negative charge on the semiconductor here, and you start accumulating holes here. So you can, this layer already has holes in it, but by applying Vg less than V flat band, you can create more number of holes at the surface here. Okay, so we call this condition as accumulation. It's already P-type, it already has holes, and you're accumulating more number of holes at the surface here. So this region is called the accumulation region of MOS operation here for Vg less than V flat band. All right. So with this background, then the MOSFETs can be depletion mode we had seen earlier, and we just saw enhancement mode. And enhancement mode or inversion mode also can be N channel and P channel, and these are the normal symbols that we use here for a MOSFET here. So note that, let's focus on the enhancement mode here. Note that it's a 4-terminal device. There's a drain, there is a gate, there is a source, and there was a body also. And so this is the symbol that we use for N channel, and this is the symbol that we use for P channel here. Instead of drawing 4 terminals all the time, we have simplified symbols here. Simplified symbol here. So this is the N channel MOSFET here. The broken line that you see here indicates that when you apply VG equal to V flat band or VG, you don't have any channel. You have to apply a gate voltage in order to create a channel here. So that's what the broken line here means. So instead of drawing a more complicated symbol, very often we draw this simplified symbol for a NMOS here. Okay. Drain, gate, the source and body. So here it's implied that the body that you see here has been shorted to the source here. Okay. All right, so this is the symbol here. So we'll use, most of the time we'll use this simplified symbol here for an NMOS here. And so note that if you look at this particular picture here, again these are simplified schematics. So we have metal, oxide, semiconductor, N plus source, N plus drain here. And to make a contact to the body, I may create a P plus layer here. Note that the body is P type. So I may create a P type P plus layer here and put a metal here. The reason why, I've said that earlier, reason why we put always P plus means a region which is heavily P type dope. The reason why we do that is that metals that you deposit here, they don't make good contact to a normal N type or a P type semiconductor. Good contact means there's very little voltage drop across it. You have to make a region which is P plus. Once you make it P plus, then the contacts become of good quality in the sense that the voltage drops are small here. So remember, in a MOSFET, we are not really interested in drops in the metal and the semiconductor here. Those drops are parasitic drops. We are not interested in that. We are interested in drops between the source and the drain. That's where the transistor action is, between the source and the drain, between the gate and the source and all that. Any drop which takes place between a metal that I put here and a semiconductor here is a voltage which is sort of wasted. It doesn't go to the MOSFET. It's just wasted at the contact here. So that's the reason why we make it N plus here and N plus. That's one reason, N plus here, and P plus also to make a contact to the body. So note that MOSFET is a planar device. All the contacts are at the top. The source, body, drain, gate, everything is at the top. Okay. This is for the P type. Similar gate, drain, source. The arrow is pointing out, and the arrow here points in gate, drain, and source here. So this is the P type semiconductor, P type MOSFET here. Now note, P type MOSFET requires an N type body. P type MOSFET requires an N type body here, right? So this is P plus, this is P plus, this is N type. So by applying a negative gate voltage, what I'm going to do is create a inversion layer of holes here, because this is normally N type. So I'm going to invert the surface and create an inversion layer of holes here, right? So now normally when I start, let's say in many of the processes, when I start with my MOS fabrication, the substrate is P type. Okay, the substrate is P type that you see here. So NMOS can be directly made. I have a substrate P type, and NMOS, all you need to do is make an N plus oxide and all that. But if you want to make a P type MOSFET, I need a N type body. So what we need to do is, you see that this whole outer region is all P type. My semiconductor is P type. So what I do is, first I create a region of N type here. This is called a specific name. We call it a N well. It's like a well that you see here. So I create an N type well inside my P type semiconductor here, N well here. And within the N well, we make a P plus and a P plus and all that, and we make the P type MOSFET here. So we start with a P type semiconductor. We create a well here, all right, of a suitable doping here, and then we do all of that here. And this is the body contact. Again, you may want to make a contact to the body of the P type MOSFET, so we create an N plus layer here, and that's where the body contact is. Okay, so that's how a P type MOSFET is fabricated on the same P type substrate. All right, so this shows a N type and a P type MOSFET side by side. See, the substrate is P type, so NMOS is made right here. N plus, P plus, this is NMOS here. And PMOS is in a separate well like this here. Okay. Now note, when I have a process like this, if I make two N-type transistors side by side, I think, do I have that? Yeah, 2 NMOSs side by side. Look at the first picture, 2 NMOSs side by side. N plus, N plus, N plus, N plus here, right? When I make that, this is a contact here. Note that the body of NMOS is, all the NMOSs is common. It's not that I can apply a separate voltage here and a separate voltage here. If I do that, if I apply a separate voltage here and a separate voltage here, you'll start getting conduction here. So you don't do that. So the body of all NMOSs is common. The voltage here, everywhere is the same. And normally what we do is, the body, we connect it to the, what is the intention normally? Is to keep all the PN junctions that you see here reverse bias. So the body P plus is connected to the most negative voltage in your circuit. The most negative voltage that is there, let's say you're operating between 0 and 5 volt. So I will connect the body to 0. So there's no chance of, because all other voltages will be positive. So there's no chance that this PN junction between N plus and P here and N plus and P, there's no chance that any of these will get forward bias. If you're operating between plus 5 and minus 5, I'll connect the body to minus 5. So and it will be connected, all of these will be connected to minus 5. So the body of the NMOSs are all in some sense all tied together, and it's a common body contact, and we keep it at the most negative contact. Look at I'm not showing certain details. For example, if you look at it, usually between which we may see later on, when you have one NMOS here and one NMOS here, we need to isolate this NMOS from this NMOS also. So normally there would be some isolation layer here. I may have a oxide at this particular point to prevent these two transistors from the drain and the source here from interfering with each other here. So there would be isolation layers here and isolation layers between the transistors here. This shows 2 PMOSs fabricated side by side. Now note, there are 2 possibilities here. To make a PMOS, I have to create an N-well. So I can create each PMOS that you see here in a separate N-well. This PMOS is in this N-well and this PMOS is in this N-well. And each one has its own unique body contact. I can keep the body at any voltage that I want, potentially. This body voltage could be anything. And it can be different from this body voltage. So for a PMOS, I have a freedom of applying any body voltage that I want, which for the NMOS I don't have. The body contacts are all common for all of them. At least in these many of these common technologies here. So that is there. There's also a possibility that I can take 2 PMOS and fabricate in the same well. I can make this well, for example, this well could have been a larger well here, extending all the way here. And so the 2 MOSFETs, 2 P-type MOSFETs, they share the same well. They're all fabricated in the same well. In that case, the body contact and body contact here have to be the same. Okay, but you have the freedom to make them in different wells, and thereby body contacts can be different here. The other thing again is that the body contact of the P-type will normally keep it at the most positive point in the circuit. This one was the most negative point in the circuit. This one was the most positive point in the circuit. So we would normally connect it to VDD. If I have operation between 0 and 5 volt, I'll go and connect the body to 5 volt. Okay, so the most positive point in the circuit would be connected to the body, so that these junctions are all the time reverse biased. Alright, this is slightly more realistic picture of how a MOSFET may look. I've been drawing, note that, go back, I've been drawing these sharp lines here. Sharp N here and sharp, these are vertical lines. One is not able to create all these vertical lines here. So this is more realistic picture. This is again a schematic drawing. This is our P-type substrate. This is the, note that source that you see here is perfectly aligned like this here to this edge. The source you cannot perfectly align. So what happens is the source extends inside the channel here and inside the channel here. Look at that. Extends here, all this here. Okay, the source extends here. This is the gate here. This is again another what we call as the spacer layer here. A small amount of this thing here. Anyway, let's not bother. Let's for the moment, let's go and understand how the qualitatively we know how the MOSFET operates. So a little bit of quantitative analysis of our MOSFET here. All right, so let's look at this particular picture here. Again, we back to our simplified schematic. Let's put some symbols here. Oxide, we'll call it the thickness of the oxide is T oxide here. And capacitance of this particular MOS system here, capacitance per unit area would be E oxide, the dielectric constant, divided by T oxide here. The dielectric constant of silicon dioxide is 3.9. 3.9 multiplied by the permittivity here. And T oxide is here. So note, this is the situation we have. A source we have grounded. To start with, drain also we have grounded. And we are assuming that this transistor has a threshold voltage of 1 volt. Okay, threshold voltage of 1 volt. Now, the inversion charge that is there in this particular MOSFET. So we are considering a case where the gate voltage node, the voltage applied to the gate here is 2 volt, threshold voltage is 1 volt, so it's higher than that. So we have a strong inversion layer here. And we have this, so note that this is a capacitor here. This is a capacitor here. So you would expect that the amount of inversion charge here would be related to Q equal to CV. Right? So normal capacitive relationship. So think about inversion layer that you see here as sort of one plate of the capacitor, and think of the metal as another plate of the capacitor. So Q inversion, we put a minus because the charge is negative, inversion charge. So Q inversion is minus Cox, capacitance, VGS minus VTH. Normal capacitor you would say Q equal to CV, right? But in this case we are saying that you have gate voltage has to exceed the threshold voltage to create significant inversion charge. So when you have VGS equal to VTH, there is a inversion charge there in my channel, but it's very small. So this is a sort of a approximate expression for how much inversion charge do I have in the channel. So we say Q inversion is minus Cox VGS minus VTH. Yes? Minus because it's negative. Electrons inversion charge is negative. If it were a p-type MOSFET, it would have been holes here. I would have put a positive charge. At VTHN, the amount of holes, the amount of electrons at the surface is equal to the holes in the bulk. Yes. Well, that's 10 to the power 16, right? Let's say if I take p-type doping as 10 to the power 16, the electrons at the surface is 10 to the power 16. But that's not enough. That's not enough. That's what we are saying. The amount of inversion charge that it will result in will be a small amount of inversion charge. Okay. When we are talking about a strong inversion layer, I'm talking about surface electron density of the order of 10 power 19. Okay, so 3 orders higher than that particular point here. So we are talking about very strong inversion layer here. All right, so this is the expression for how much inversion charge do I have here. Now note that this is inversion charge per unit area. Inversion charge per unit area, because this is the capacitance. I've not multiplied by the area. So this is capacitance per unit area, and the inversion charge also that I get is per unit area. Okay, and this inversion charge that we are saying is like a sheet. It's like a sheet of electrons. Okay, very, very thin thickness of the order of a nanometer, very thin sheet of electrons exists at the surface. So that's the view of the inversion mode or enhancement mode MOSFET that we have. Very thin sheet of electrons at the surface. How much charge will be there? Well, we can calculate. Cox, VGS minus VTH. That much amount of charge would be present. So if you increase the gate voltage to a higher value, you'll get higher amount of inversion charge. If you decrease it, you'll get smaller. And this equation predicts that at VGS equal to VTHN, the inversion charge is 0, but keep in mind, it's actually not 0. There's a small amount of inversion charge. So this equation, as you get very close to VTHN, this equation starts to break down. It's no longer very accurate. But as you go much above VTHN, this equation is reasonable. Okay. All right. So that's when I've not applied any voltage at the drain, source is also grounded. Okay. Next, note that what I've done is I've applied a small voltage, 0.5 volt here. Now note, when I apply 0.5 volt here, the voltage at this end this N plus is connected to ground, so the voltage at this end will be 0, ground. The voltage at this end, which is connected to 0.5, will be 0.5. Because N plus is a heavily doped layer, there's not much voltage drop here. So if you apply 0.5, the voltage here would be 0.5. So what happens is you have 0.5 at one end and you have 0 at the other end. And so what would happen is the voltage in the channel will start from 0.5, will become 0.4, 0.3, 0.2, 0.1, and eventually come to 0 here. The voltage along the channel is varying now. I have different voltages along the channel here. And that's why the channel voltage is what we're calling it as Vx. Earlier the channel voltage was, remember, it was 0 here and 0 here. So the channel voltage was 0 throughout. But now I apply 0.5 volts, so it will be 0.5 here and the channel voltage will be different here. Now, very interesting consequence that occurs is, note that the amount of inversion charge is a capacitance. Cox, earlier we were writing Vgs minus Vthn because the channel voltage was 0. Now there is a voltage on the opposite plate. Right? We are thinking of inversion layer as the opposite plate of a capacitor. And that opposite plate has a varying voltage. It's not a metal. If it were a metal, it would have had the same voltage throughout. So it's not a metal. It's an inversion layer according on which the voltage drop can occur. So you have 0.5 here and you have 0 here. So the voltage along the channel is varying. So the inversion charge is also varying. Where would the inversion charge be maximum? Here, at the source end. Why? Because Vx is 0 here. The source is connected to 0. Maximum inversion charge occurs here. And minimum inversion charge occurs at the drain end. Okay? So, this is the picture. So, remember this equation now. Q inversion is minus Cox, Vgs minus Vthn minus Vx. Vx is the channel potential here. So, this is at 0, 0. 0 volt here and 0 volt here. Alright, I'm not showing the full MOSFET here now because the inversion layer, as I've been saying, is of thickness of the inversion layer is of the order of a nanometer. Okay, so it's very, very thin inversion layer here. While these regions are much, much thicker here. Okay, N plus would be maybe 100 nanometers or 200 nanometers depending on the technology here. So for 0.5, schematically representing it like this here. Right, we just said more inversion charge here and lesser inversion charge here. And showing that the inversion charge is decreasing. All right, so all that, this is a schematic simply illustrating that the amount of inversion charge here is large and the amount of inversion charge is smaller here. Don't think that the thickness and all that is changing. I'm not implying anything about the thickness of the inversion layer here. I'm only implying the amount of inversion charge by this particular diagram here. Okay, thickness is very, very small, so don't worry about the thickness side here. As I said, as far as thickness is concerned, think of it like a sheet. Okay, it's like a sheet of electrons. Okay, and so all that we are saying is more electrons here and less here. Now, if I apply 0.8, note that nothing changes here, right? Amount of inversion charge here remains the same according to this equation because Vx at the source end is always 0. At the drain end, note that it has become even smaller. Now I apply 1 volt. What will happen when I apply 1 volt? Note that this is, Vgs is 2 volt I apply, Vthn is 1, 2 minus 1, and when I apply Vx is equal to 1, goes to 0 here. So we call this particular point as that the channel has been pinched off. Channel has been pinched off. Almost like the entire charge from the channel has been removed. Now note that we don't totally remove it. These are all approximations. Okay, we don't totally remove it, but there's a small amount of a charge, but we say most of the channel has been removed from that particular point here. So note that by applying increasingly drain voltage, gate voltage is the same, 2 volt, 2 volt, 2 volt, 2 volt here. But as you apply higher and higher drain voltage, note that what is happening here. The amount of inversion charge decreases here and elsewhere also in the channel, except at this particular point. At this point, the inversion charge is the same in all cases here. Everywhere else, the inversion charge is changing. All right. Now, how do we think about the current? How does the current flow in a device? All right. So again, note that one of the challenges of talking about this particular topic is that how to talk about it in a meaningful manner in as few lectures as possible, right? So that's if I had more lectures, one can go in more detail and it would be more satisfying for you, so you'll understand it better. In this case, we have very little time, and in that very little time, how do we understand it without getting confused about it? So a simple way of thinking about your MOSFET is note that you have an N plus layer, and you have a sheet of electrons. So think of it as a resistor. As a very simple way of thinking about a MOSFET is a resistor. Now resistor, as you know, resistance is rho L by A. Right? Rho L by A here. And I can write now, in general, resistivity is what? Resistivity would be 1 over Q times mobility times the electron density. Okay, so resistivity of that kind here. And electron density may be varying as a function of position. So it's like a resistance, but with a different value of, different values of resistivity at every point. Because the amount of electrons is different at every point here. In general, when you apply a drain voltage here. So it's not resistivity is not the same throughout. Resistivity is different at different places. Minimum resistivity here and sort of maximum resistivity here. Okay. So it's like a resistance here. And in this case, well, when I don't apply any voltage here or voltage is 0, I will have a uniform channel. Q inversion would be the same everywhere. And because I have not applied any voltage here, so my drain current will be VDS, the voltage applied. So this is my reference here, source. All voltages for the time being, and body is supposed to, I've also grounded here. Okay, so body is grounded, source is grounded, so our reference is that. So if I don't apply any voltage between drain and source, so VDS is 0. And there is a resistance here, R channel, and obviously current is 0. If I don't apply any voltage to a resistor, current is 0 here. So that's not a problem. When I apply a voltage here, 0.8 volt. Now note, if you compare these two cases here, case this and this one, in which case overall resistance will be higher, or will it be the same? Compare this one versus this one. Where will resistance be higher? I've applied 0.1. No, overall resistance. Overall resistance in the channel. Obviously in this case, because when I apply 0.8, note that the amount of inversion charge is decreasing. And here the inversion charge was, both have the same gate voltage. Right? So inversion charge is obviously less here. At the source end, the two are the same. But at everywhere else, the amount of inversion charge is less. And if the charge is less, then the resistivity is higher. I said the width, don't look at it. This width is just a schematic drawing. To illustrate, this diagram only illustrates that the amount of inversion charge is less. Width has got, it's like a sheet. Width has got nothing to do with it. There's no width information in this particular diagram. That's why this diagram can be confusing. Don't talk about width. Okay. So the resistance here would be higher. Right. So our channel is greater than the original channel resistance here. IDS is VDS by R channel will obviously be greater than 0. I've applied a voltage here and there is a resistance here and some current would flow. Right? Some current would flow. Now interestingly, suppose I put here 0.5 volt here. Okay, so let's go and see. So as drain voltage increases, two things happen. Channel resistance also increases here. Higher, so if I put 5.5 volt here, what would be the channel resistance for 0.5 volt compared to channel resistance for 0.8? Channel resistance for 0.5 volt would be less. But what would happen to the current? In which case current would be higher. In one case, the channel resistance at 0.5 volt is less, but the drain voltage is also less. In the other case, the channel resistance is higher, but the drain voltage is also higher. Right? So, but the way current flows is like this here. This shows the current in the MOSFET. Drain current, this is the drain current here, plotted, versus the drain to source voltage here. And note how the current flows. So drain current versus drain to source voltage here. Note that, a straight line would have implied what? Like a constant resistance here. But we note that as we apply a higher and higher drain voltage here, what happens to the resistance? keeps on increasing. Because resistance, go back and see, as you apply higher and higher, the resistance of the channel, overall channel, will keep on increasing. What does that mean in terms of the diagram here? That the slope will keep on decreasing. The slope of this particular line here will keep on decreasing here, right? The slope will keep on decreasing, indicating a higher and higher resistance. So that's why the MOSFET is like a resistance in this region here. It's like a resistance, but it's not a constant resistance. If it were a constant resistance, it would have followed this straight line. And therefore, what happens is it goes here and keeps on bending. Bending indicating the resistance is higher and higher. It keeps on going like this here. Eventually, a stage comes at this point, right, where you see this leveling off. A stage comes where, which we call as the saturation voltage. It's obvious why we call it the saturation voltage, because the current is no longer increasing. It sort of flattens out. And where does this occur? Where would you guess? At the pinch-off point. In the simplified case, where the channel gets pinched off. So remember, as I'm applying higher and higher voltage, the charge near the drain keeps on decreasing. Eventually, you reach a stage where the charge near the drain is practically zero, very small. And at that point, it levels off and becomes constant. And the voltage at which this occurs is, we call this as the VD sat here. So this is the region which we call as this, why it flattens. I'll attempt a very simple explanation, see if it makes sense. So why this region here, as its name indicates, is called saturation. And this region is called the sort of linear, because this is where it is linear. But in analogy with the pre-transistor era vacuum tubes, so we also call this as the triode region. So you'll hear these words, linear region, triode region, for this part of here. But note that it's not linear, as you can see here. It's only linear very, very close to the origin here. You can think of it as linear, okay? But in this region, the MOSFET is acting as a resistor, although with a non-linear resistor, with this resistance changing with voltage here. So you can think of MOSFET as a resistor. In this case, what should you think of MOSFET as? No, current source. See, whenever you have a current here, which is not changing with voltage, it's a current source. So in this region, the MOSFET acts as a current source. Constant current. This is a reasonably flat characteristics here. So it's a current source, and here is a non-linear resistor. And it makes a transition from a non-linear resistor to a current source here. And this is, one source of confusion often is in a bipolar. If you recall, we also had a diagram like this. We used to call this region as saturation and this region as active mode. So here, this is the saturation region, and this is also the active mode, by the way. We will call this also the active mode in a MOSFET here. Active in the sense that, when I want to make an amplifier, I will bias my MOSFET in this region here, where MOSFET acts as a current source. Same, remember, bipolar transistor was also biased in this region where the region characteristics was flat here. Okay? So this region here, the beginning of this particular region, saturation, occurs at a voltage called VD sat. And VD sat is equal to VGS minus VTHN, the place where the channel gets pinched off. Okay? So for a MOSFET, there's a well-defined quantity called threshold voltage. For us, we were taking it as 1 volt. So if I have 2 volt VGS, then 2 minus 1, the VD sat will be around 1. Yes. Okay, all right. So I know that there is a lot of confusion here. What happens there? Okay. All right. So let's go back and see here. So this is what we are calling, right? We are applying a voltage 1 volt here, and this is 2 volt here, and we are saying that a pinch off occurs at this particular point here. And note that now this region is, I'm saying the Q inversion is 0 here, but I also remember said also that this equation tends to break down when you start approaching Q inversion equal to 0. So it's no longer correct. So all that we are saying by pinch off is that the region has small carrier density. We are not saying it's 0. We are not saying it is 0. 0 carrier density would obviously imply then the current cannot flow. So we are not saying 0, we are saying it's small. It's a very small carrier density here. Also note that, as I've been saying here, that the resistance, because the carrier density is high here, this region would be a very high resistance region. If I take, let's say, the whole region from here to here is 1 micron. The whole channel length is 1 micron. And I divide it into 0.1 micron element. So 0.1 micron element here. So if I look at the resistance of that 0.1 micron element here versus 0.1 micron element here versus a 0.1 micron element here, you will find that the resistance of this particular region would be very high because the carrier density is very, very low. Right? Okay. So why does the current saturate? All right. So let's see if it makes sense here. Why does the current saturate when I approach towards the pinch-off point here? So let's go to the other extreme where the voltage applied is very low. If the voltage applied is very low, what do I have? Uniform channel everywhere. And I'm saying that my entire channel, I'm breaking it up into small elements just to understand it. So I have R, all that, right? If so at zero bias, I have the same resistance everywhere. If I divide my channel into small elements, same resistance everywhere. If I increase my drain voltage by a certain amount, let's say I go from 0 to 0.1 volt. How would that voltage drop? Delta VD. So initially it was 0, and I go from 0 to 0.1 volt or 0.2 volt. How would that voltage drop? It would equally distribute. It would equally distribute all throughout, right? Because each one of them is the same series resistances. So 0.2, if I divide it up into 10 elements and I apply 0.2 volt increment here, 0.2 divided by 10, right? So it would be 20 millivolt drop here. How much will the current increase? So the voltage, let's focus here. The voltage increment would be how much? 20 millivolt. 20 millivolt divided by R would be the increase in the current. So my drain current would increase by 20 millivolt divided by R. Right? Okay. Now let's go to the other extreme. The other extreme is I've gone towards the pinch-off region. I've gone to a region which is like pinch-off. And at this end, remember, at this end the resistance is still R. Because near the source nothing changes. So this element is R. And at the pinch-off point I've arbitrarily put 100 R. You can put 1000 R depending on how large the resistance became. 1000 R or 100 R. Correct? Because it's a very low electron density is there and the resistance of that particular element will be very high. Now do a 0.2 volt increment here. 0.2 volt, increase the drain voltage by 0.2 volt. What would happen? Where will it drop? It will all drop here, right? How much will be dropped across this? Negligible. And if negligible drops, the negligible drop divided by R is the increase in the current. So how much would the current increase? Negligible. So once you create a very high field region, all the extra voltage is dropping here, nothing is reaching in this particular part. And the current tends to saturate. Current doesn't increase. Okay? So that's the reason why we are saying is once you create the pinch-off point here, let's see if, okay. So once you create the pinch-off point here, you create a high field region here at this particular point. All the voltages are dropping here, nothing reaches all this region here, channel. Nothing reaches here, or very little reaches here, and the current saturates. Again, this is a very simple explanation. One has to go into more details and see what is happening at this particular point, which, you can do that later on. All right. After pinch-off, something very interesting happens. Once the pinch-off occurs, note that we go back and see after the pinch-off occurs, the drain current is no longer responding to drain voltage. Any change in drain voltage is no longer changing current. So now what is interesting is the following. After pinch-off or saturation, drain current does not change much with drain voltage, but is still very sensitive to gate voltage. Because as you change the gate voltage, what will it do? It will change the amount of inversion charge. And as it changes the amount of inversion charge, the current changes. So this is where you end up with a region. Once you bias the MOSFET in saturation region, what you end up with is drain current is very sensitive to gate voltage. Drain current is not sensitive to drain voltage at all. So transconductance becomes much larger than output conductance. And now your device becomes capable of amplification in that region here. So I have to go in this region, the device will not amplify. Because I have transconductance, but I have output conductance also. Drain is responding to the drain voltage also. it is not going to respond. It's not going to amplify much here. So I have to go in this region here. And once I go into this region, then my MOSFET is capable of amplification. Okay. So drain current much larger than gate. So I obtain, at least in a part of the characteristics, where this relationship is satisfied here. So again, the voltage at which pinch-off occurs is the drain to source voltage. Saturation voltage here, inversion charge is going to 0 at this particular point, and VD sat is VGS minus VTH. And so it's an important parameter here, because to bias the transistor in saturation region, I have to know what is the boundary between the linear and the saturation region. So this is the boundary here, VGS minus VTH. Okay. All right. This, as I said, reminder. This is a very simple picture. Simple picture. As the MOSFETs become smaller, saturation and all that are more complicated. How does the current really flow here? Okay, those are complicated things. We'll not get into that here. Now, what happens if I apply something larger than the saturation voltage? Right? So saturation of pinch-off was occurring at 1 volt. Now I have applied 1.5 volt. What happens then? So note what the pinch-off point, the place where I'm saying Q inversion goes to 0, moves towards the left here. Earlier pinch-off was occurring here at this point. When you apply even 1.5 volt here, the pinch-off point moves here. Right? And what is the voltage at this point? The pinch-off point is where this inversion charge for us goes to 0 here. Okay, so the pinch-off point moves here. The voltage at this point will be how much? When you apply 1.5 at the pinch-off, the voltage has to be 1 volt. So at this point, the voltage is VD sat is 1 volt here. And so this is the very high field region here. So 1.5 you applied here, pinch-off is occurring here. And so 1.5 minus 1.5 volt is dropped here in this particular region. And it's a high field region, it's a very narrow region. Okay, I'm just exaggerating this to illustrate it. Okay, so what happens is now, if you think about, we have an interesting case of what we call as channel length modulation. All right, so anyway, let's stop here, we'll discuss that.